Hi, my name is Warner and I'll be your chemistry tutor for this problem. Let's start by reading the question and underlying key details they're gonna help us answer the question. So we're trying to determine the element with the lowest atomic number that has a half-filled D subshell in the ground state. And the student has problem understanding the quantum numbers of electrons in atoms. So let's start off by having a discussion on what do we really mean by a quantum number. So quantum numbers allow us to describe the trajectory or movement of an electron within an atom. There are four different ways. We could describe the shell, the shape of the orbital, the numbers of orbitals within that certain shell, and the direction of electrons. So in other words, it could be the principal quantum number by n, the orbital angular momentum number by L, magnetic quantum number by ML, or the electron spin quantum number by MS. So let's consider n equals 1. So when we're trying to describe the shell or the distance of electrons in when we're considering n equals 1, it's going to be the volume of the sphere around a three-dimensional coordinate system. So we can say that the maximum distance of where an electron can exist would be from the nucleus itself towards the outermost part of the sphere. And the probability of finding an electron would be within the volume of the sphere. So what about the shape about the orbital when n is equal to 1? There could only be one shape. Why? Because L is defined by n minus 1. So it's going to be 0. The number of orbitals is going to be, it's just going to be only 1, right? Because if it's 0, it could be described as, um, let's say in the case of hydrogen, it's going to be one electron occupying the 1s orbital. So there's only one orbital for when n is equal to 1. And the spin quantum number, since the electron is pointing upward, we can say it's going to be positive minus 2. If it's in the case of, let's say, helium, so we realize it's pointing downward, so it's going to be minus a half. So what about when n is equal to 2? So let's try to understand like what kind of shape we're talking about. So let's find out what L is in this case. It's just going to be 1. Interesting. So what about the number of orbitals? So it's going to be the range from -1 to 1 as described by this equation here. So it's just going to be minus L between whatever numbers to L. And this is simply described as the p orbital here. So the magnetic quantum numbers designate to certain orbitals. This is 0 here. So let's say in this orbital, it's going to be associated with x, the x-axis, y-axis, and z-axis. So let's start by drawing them out. Let's use a specific color here. So the p orbital with x, the the p orbital with respect to y, messed up there, and the p orbital with respect to z. So with the magnetic quantum numbers, we can determine which certain axes. Let's say if the electron is occupying only the first orbital, we could say it corresponds to the x orbital, and the electron spin number, since it's pointing upward, would be positive. If it's corresponding to the z orbital, then it would be occupying a magnetic quantum number of 1, and it would be basically the yellow orbital here. So let's consider when n is equal to 3 with respect to the d orbital. So when we're talking about period 4, there's going to be 4s 4p, and the 3d orbital. And we're focusing solely on the 3d orbital. That's why we're considering only n equals 3. So in the d orbital itself, we realize that transition metals are occupying the d orbitals here. So since we're trying to, the question is asking specifically on the lowest atomic number, we have to consider the shell where the d orbitals are lowest. It's going to be 3d. So we're trying to find which specific element has a half-filled d orbital. So we can do that by writing down the electron configurations of each of the transition metals are occupying the 3d orbital. So there are certain exceptions here. So we see that it's going to be D1, D2, D3, whoa, D5. So chromium is currently within an excited state, and that's going to be the most preferred state as opposed to saying D4, 4s2. So it's important to realize that there are going to be exceptions when it comes to the electron configuration descriptions for the transition metals. So then manganese is going to be D5, 4s2, going to incremental order. Then there's going to be another exception with copper because there's another certain excited state. So when we're saying half filled d orbitals, we're basically saying when it has this certain configuration. So let's say this is D. It's going to be XY. Let's say XZ and YZ. X2 minus Y squared. It's going to be Z squared. So let's start off by writing the the quantum numbers for n equals 3. So we see that L is going to be simply n minus 1. L is equal to 2. What about the magnetic quantum numbers? So there's a specific range, minus 2, minus 1, 0, 1, 2. So each of these numbers corresponds to a particular orbital within D. Minus 2, minus 1, 0, 1, 2. So when it's half filled, it's going to be corresponding to z squared. So we realize that the magnetic quantum number associated with a half filled is going to be 2. And the electron spin number, ms, is just going to be positive, 1.5. And this is all describing chromium. So that's our answer. So the element where it has the lowest atomic number and has a half-filled d orbital would be chromium, and atomic number is just simply 24, which is just the number of protons. So in summary, when we're thinking of quantum numbers, we have to describe the quantum nature of electrons in an atom. So we can do that by 4 different ways. We can use the principal quantum number n, angular quantum number, which is L, the magnetic quantum number ml, and the electron spin number ms. So through knowledge of electron configurations, we can make our lives easier in terms of describing certain orbitals. So in the case of chromium, we realize it's going to be 3d5, 4s1. So when we're solely focusing on the d orbitals, we realize that there's going to be 5 electrons occupying it. So it's going to be half filled. So from quantum numbers, we can identify specific electron configurations and thus the element itself. So if we associate this d orbital with the electron configuration, we can associate this electron configuration with the element itself and the atomic number, which is going to end up 24. So I hope you found this video helpful in terms of finding the lowest atomic number in terms of the half-filled d orbital. If you have any questions, if something remains unclear, feel free to let me know. Thank you. See you later.